CHEM1112 students, good morning again. This is Dr. Jingbo Louise Liu from Chemistry Department of Texas A&M University, Kingsville. So today we will discuss Experiment 3, Determination of Equilibrium Constant. The objective for this Lab 3 to use a spectrophotometer to determine the equilibrium constant of your chemical reaction, to use graphing techniques and data analysis to evaluate your data. And also we are going to determine the equilibrium constant for a soluble substances which is reaching the equilibrium. So that's the three goals of this reaction. So we are going to give you a brief introduction about the equilibrium. So as you already knew, the equilibrium applies to the extent of a reaction, the concentration of your product that has appeared after an unlimited time, or once the concentration of your product has no further changes. At this point, we call the dynamic equilibrium is reached. At equilibrium, your reaction rate for the forward direction is the same as the reaction rate for the reverse reaction. The system at equilibrium is a dynamic equilibrium on the molecular level, even though you did not observe further net changes, but you are going to observe the changes from both direction, I mean forward and reverse direction. So in this case, your changes in one direction are balanced by the changes by another direction. So this is called equilibrium. At equilibrium, the forward reaction rate is the same as reverse reaction rate. If you have your forward reaction rate equals to reverse reaction rate, you are going to derive the rate law. Both rate law tells you the equilibrium both rate law related to the rate constant and the concentration. Further, you can use the reaction rate constant for forward divided by the rate constant for reverse reaction to determine the K. This capital K represents the equilibrium constant equals to the concentration of your product to the power n divided by the reaction concentration of reactant concentration to the power m. Be advised, this power n, they are possibly related to your concentrations. Your previous study, your P and Q in your rate law determination, they are not related to coefficiency. So the values of n and m are the coefficiency of your chemical reactants or products after you balance the reaction. And the equilibrium, this K is the equilibrium, capital K, not related to your kinetic, not calculated by your kinetic study. The reaction rate for forward and reverse are equal, but doesn't mean concentration of reactant and products are equal. No net change, but they are not equal to each other. Your K can be big, can be small, can be intermediate. How do you determine concentration during different reaction time? We are going to indirectly determine the concentration of your product or reactant using a spectrophotometer. This diagram is a very simple spectrophotometer. This spectrophotometer is an instrument to measure the light intensity at a specific wavelength. In our lab, you need to fix the wavelength for the particular chemical reactions. Different chemical reactions, they are going to result in the light absorption at different wavelengths. You need to know that wavelength number. You need how many nanometers. You figure it out. This spectral photometric analysis is involving in the interaction of your electromagnetic radiation with your substances. So in our case, we're particularly involving in possibly in UV light and visible light, particularly in the visible light in your case. This diagram showed you electrochemical radiations. So you can see from radio frequency and to the all the way to the microwave and infrared, UV light with ultraviolet, X-ray and gamma ray. So you can see our visible light is in a very small portion, 380 all the way to 800 nanometers. And about the characterization in this case, you are going to use the absorption A equals smaller a times B and times C. So in that equation, you call the Lambert-Beer's law. This one tells you when you measure the absorbance by the different species, the concentration is a very important factor. The higher the concentration of the absorbing species in your sample, the more electromagnetic radiation will be absorbed. The higher the intensity is for the complementary transmitted radiation. Several factors control the amount of electromagnetic radiation, so in the sample which absorbing the light. First one called the molar absorptivity coefficient. You have different substances. The different substances have different molar absorptivity coefficients. The second variable is the thickness of your sample. In this case, you are going to use a liquid sample. You place it in a cuvette. The distance between the two planes of your cuvette is the thickness of your sample, also is the pathway of your light. And the concentration of the absorbing materials is what you are going to study. Again, as we mentioned, we use Lambert-Beer's law. This Beer's law showed capital A absorbance equals to smaller a times B times C. Capital A represents absorbance. You can use T as your transmittance. Smaller a represents molar absorptivity coefficient for the substances at a given wavelength. The B is the thickness of the absorbing substances in centimeter. The molar concentration of your absorbing substances is in mole per liter. In your particular experiment, what you are going to do, you are going to choose your wavelengths. I believe it's 447 nanometers. You are going to use a cuvette with the length of 1.0 centimeters. And then first of all, you are going to do the calibration curve. You prepare different concentrations. You measure the absorbance for the different concentrations. You apply this. You plot a graph using absorbance as y, concentration, molar concentration as your x. Absorbance is a unitless value, and then you are going to derive your A and B. In this case, your AB absorptivity times the diameter of the distance between for your cuvette, between the two planes of your cuvette, the thickness of your cuvette will be constant. What you are going to study only A and C. After you plot this calibration curve or standardization curve, you can measure the A and then you derive your concentration. From there, you are going to determine your equilibrium constant. What you are going to do, you are going to use this ferric ion 3+ reacted with thiocyanate SCN negative. You are going to produce a thiocyanate ion. This reaction is going to allow you to calculate K. Your K, equilibrium constant based on concentration, expressed by the concentration of your product. divided by concentration of two reactants. The solution of your Fe3 plus and thiocyanate will be prepared. You are going to know the concentrations of these two reactants. In your reaction, you are also going to use large amount of ion 3 plus. Ferric is in large excess, meaning your reaction must be forced into the right. Your equilibrium is going to be forced to the right. What does this mean? Meaning at equilibrium, the concentration of your thiocyanate will be the same as your cyanoto ion. These two concentrations will be the same at equilibrium, and then you are going to do the calculations. So your K, capital K, is a constant value for a particular chemical reaction. This K has different magnitude. The magnitude of K indicates your reaction direction. For example, if you have a very, very large K, your K is so large, meaning all the reactants becomes to your product. This large K represents the forward reaction is favorable. If you have a very small K, meaning your reactants maintain only a very small portion becomes to product, meaning reverse reaction is favorable. Or sometimes we say there's no reaction. No reaction is what we are calling. So K is so small. If you have an intermediate K, such as your K is 0.01 to 100, so you consider this reaction reaches the equilibrium, meaning you have reactants, you also have products. Again, concentration of reactants and products, they are not necessarily to be the same. They have no net change, but doesn't mean they are going to be the same. You are going to do two parts. You are going to do the standardization. So you use different standard solutions, you prepare them, and then you are going to do the calibration, choose the wavelengths at 447 nanometers, and then you are going to plot a graph using A as your Y, using C concentration, molar concentration as your X. This is your standardization curve. Second point, you are going to measure the absorbance of the different concentration of your solution. After reaction, you no longer know what's your concentration. You are going to do this preparation of your solution. And then from these different concentrations, you can measure the A. You already measure it. I suggest imagine you prepare 5 different solutions and then you measure 5 A's. You are going to derive the concentrations, and then you are going to use the K equals to the concentration of product divided by concentration of reactant, which is called the mass law, to determine the equilibrium constant K. So that's essentially what I want to show you, and the detailed procedures has been described in your lab manual. The lab manuals for the experiment number 1, number 2, number 3 have been posted under your blackboard with the permission from the McGraw-Hill publication company. From there, you need to buy the electronic lab manuals. So you need to buy the lab manuals to understand what's going to happen for your lab 4, 5, 6, all the way to lab 10. Again, that's all for today. You have a beautiful day. Stay safe and stay healthy.